Branch line maps are really useful things for exploring the three-dimensional structure of linked thrust systems. And in this video, we'll look at how we can construct them. But first of all, what are branch lines? Well, on this block diagram, I'm showing the surface geology, such as we might see on a conventional geological map, and we've seen two thrusts which join, and they define a thrust-bound slice. So let's move into the subsurface, and we can take the upper thrust and project it down and show the extent of our thrust-bound slice in the subsurface. Well, of course, this geology didn't just extend here. Before the area was eroded, it continued up into what is now the air. So our thrust-bound slice had an original extent like this. The branch line is where the two thrusts join, and they join in 3 dimensions like this. And effectively, the branch line is the limit to our thrust-bound slice. In other words, it's the slice's zero isopac. Outside this blue line, the thrust slice doesn't exist. Inside, it very much does exist. So that's our 3-dimensional representation of the branch line. And to create a branch line map, we just take this representation and project it onto the plane of the map. So anything in the subsurface moves up to the plane of the map. Anything that's been eroded moves down onto the plane of the map, like this. Let's just take this branch line away and we'll come back and construct it. So here's our thrust-bound slice showing the map view. And there are 2 places where the bounding thrusts meet. Here. These are called branch points. They're points on the branch line. Now let's look at just a segment of the branch line here. And we can see that our branch line segment changes from being underground to having been eroded and above ground as it passes through the branch point. Now let's put the whole of the branch line in. Well, we can consider this loop rather like a joined up piece of string and consider the topology of the line itself. And the topology of continuous lines crossing an interface, a branch line crossing the map surface, is that there must be an even number of places where our line crosses that surface. In other words, there must be an even number of branch points on a complete geological map. And the behavior of our branch line changes from being above ground to below ground. In other words, it changes from being eroded to being buried as the branch line crosses through a branch point. Therefore, our branch line map should show segments that alternate from being above land surface, in other words eroded, to below land surface and therefore buried. So our map should look something like this. Okay, so now let's take these ideas and apply them to a rather more complicated geological map. Okay, now let's add the geology. So on this map, well, let's zoom in and we can have a look at what it shows. So here's a zoomed in area, and we've got 2 distinct thrusts, one marked with triangles, the other one marked with these brick ornaments. And these 2 thrusts contain a slice of rock, a thrust sheet. Now this is a conventional representation, so the teeth ornaments are shown on the hanging wall side of the thrust. So in other words, our triangle thrust sheet is the one on top. And underneath this, in its footwall, is the brick thrust, and underneath both is a common footwall, which I've coloured up with that pasty yellow colour. Okay, so that's the map of the thrusts. Here's our thrust-bound slice, and we can trace it along and see that it tapers out where the 2 thrusts meet, and that is a branch point. And our mission now is to construct the branch line for the whole map. And in doing so, we'll establish the limit of the slice of rock that's bound between the 2 thrusts. Well, a useful thing to do first of all is to find all the branch points. And the easiest way to do that is simply to follow one of our thrusts out. And I've just picked the triangle thrust and illustrated this in red. And now we just have to walk around all the red outcrops and make sure that we collect all the places where the 2 thrusts join. So let's start with the main trace of this thrust, which runs right across the map here. And we can now see 2 places on it where the brick thrust joins the red thrust here. So we found 2 branch points. Okay, now let's move to the bottom of the map where we've got two windows, in other words, holes through the upper thrust sheet that reveal the rocks below. And down on here, we can identify 4 places, 2 in each window, where the 2 thrusts join. And now let's move to the northern part of the map. Here, where we've got a patch of rocks that's detached from the main outcrop traces of our thrusts, therefore it's a tectonic outlier or clipper, and we can see that in this clipper there are 2 places again where the 2 thrusts join, here and here. So those are all the branch points. We can just make sure by checking around the rest of the map, and yep, I think we've got them all. So we've got a bunch of places where our 2 thrusts join, and we've identified those. We've found the branch points. Our mission now is to join these up into a single continuous branch line. In doing these sorts of exercises, I find it really useful to sketch out little cross sections to show the relationships between the different units. So let's start off here, and I'm just going to sketch up a cross section through X and Y to show how the units relate. So here I've drawn the red or triangle thrust running between X and Y. You can see that on the line of section there are 2 outcrop patches of the thrust sheet that are broken in the middle or eroded away, which is shown by that broken red line. What about the brick thrust? Well, that only lies on the map, you can see, towards the Y end of our section line. In other words, it lies over here, and it doesn't appear on the other side of the clipper. Therefore, the 2 thrusts must join beneath the outcrop of the clipper, there. In other words, this segment of the branch line is buried. Well, we can take this information and put it back onto the map, here. So within the clipper, the branch line segment is buried. Okay, now let's turn our attention to another part of the map. We can move over to the next collection of clipper, which lies slightly to the east of the section we've been looking at already, over here. And let's draw our section now, XY, in this sort of orientation with a dog leg that kinks through a little patch of the red thrust sheet. Here is the profile, and you can see that little patch of red that lies between the 2 main traces of the main red thrust, one towards X and the other towards Y. And of course, originally this all joined up like this. So there's segments where the thrust has been eroded away. Okay, now let's put on the brick thrust that lies underneath. And we can see that it doesn't exist all the way beneath this thrust sheet. On the X side of our section, again, the underlying thrust, the brick thrust, doesn't exist on the map. Okay, this exerts a pretty powerful constraint on how this black line on our profile, the brick thrust, joins up. It must join up like this. In other words, the 2 thrusts must join here, and that segment is up in the air. So here we've got a branch line segment that is eroded. And we can take this information again and put it on our map, there. And you'll see that this time our branch line segment lies outside this particular clipper. Okay, now let's turn our attention to another part of the map, and I'm going to move down to the bottom end here where the windows are. And what we're going to do is draw a cross section through one of them. Well, let's just pick this one over here, the western one, and we'll draw a section XY. Here's our profile. So we can see the window has excavated a hole through the upper thrust sheet. Outcrops of the red thrust lie either side of a valley, and presumably they joined up across the top of the valley but have been eroded. So what about the underlying thrust, the brick thrust? Well, this lies only on the Y side of our window, here. It doesn't lie on the X side, therefore the 2 thrusts must join up in the air, here. So there's our branch point. It's been eroded. So this branch line segment in this particular window has been eroded out. There, and that's where it plots, somewhere in the window. What about the other window? Well, it's going to behave very similarly. So we're going to have another segment of the branch line over here that's also been eroded. So we're now getting a bit of an idea of how the branch line must run. Let's now think about the characteristics of these branch lines, and in the pattern we've looked at already, we can see in the window here, we've seen that our branch line segment is eroded. And so too is this one in this window over here. Okay, now let's see if we can join these up. And we're going to track the segments that are eroded and the segments that are buried. So here's a loop for the southern part of the map that links up the two windows. And the segments that are in the windows themselves have been eroded. Therefore, the segment that links the two windows here must be buried as the branch line crosses branch points. Okay, and we can continue to join up the branch line to the other two branch points here. We're going to try now to link across to the clipper, to here. So we can do a loop like this. Now, in the clipper, of course, that we looked at, we saw that the branch line segment here was buried. Therefore, this segment on the map is a buried segment of the branch line. So can we connect our areas together? We can. This segment must be eroded now as we come out of the clipper. Then as we come round to the left-hand side of our branch line in here, as we cross the branch point back towards the windows, then in here, it must be buried. And indeed, it must be buried on the other side of the map. So we're picking up the behaviours of our branch line as we go around the map. Finally, let's complete the loop here. And we can see in this segment in here, the branch line, remember, was eroded. So that's the branch line, complete and characterized by being either buried or eroded. So we're now going to check these behaviors, the topological constraints. Remember, there should be an alternating buried versus eroded segment behavior and therefore an even number of branch points on our map. Well, let's check. So let's check first of all the even number of branch points. We can count them off. 1, 2, 3, 4, 5, 6, 7, 8. Yep, that's it. So 8, an even number of branch points. So that check has worked. Now let's check that everything's alternating, buried to eroded as we move around the map. Put our behaviors back on again. And yes, it does. That each segment alternates with the next, eroded, buried, eroded, buried, eroded, buried, eroded, buried, as we go around the map. So the topology works. Finally, have we incorporated all pieces of the thrust slice that lies between the two thrusts? Let's zoom in to this area down here. And we can see that as I've drawn the branch line through there, there's a piece of the brick thrust that lies on the left-hand side, therefore within the branch line loop here. So that clipper of the slice of rock that lies between the two thrusts lies inside the branch line. Conversely, here we've got a clipper of the red thrust sheet that lies directly on the common footwall and therefore lies outside the branch line. And finally, down here, there's a little window where we see through the upper thrust sheet, again, directly onto the common footwall without that slice between. So that lies outside the branch line. So there is our complete branch line map. We've assessed it for topological correctness and to see whether it honours this idea of containing all pieces of our thrust slice. Branch line maps like this are really useful. If we're going to draw a cross section through here, we're defining the extent of our thrust bound slice, and we can also show how far we can correlate it. In other words, it only extends within this loop, not outside it. So really useful ways of exploring the three-dimensional structure of linked thrust systems. Branch line maps.